All right, so we start off with a practice of a graph that you already know. Well, we're going to be building on it. And the information we know about it up here is actually going to be really useful. Like the asymptote. Well, notice this graph has been moved up 1. So our asymptote's going to be up at 1. Knowing that, we can then know that our domain is all real numbers, because the domain of every exponential is all real numbers. And that the range needs to be the y values that are greater than 1. Because remember, it always has to be on one side of the asymptote. And since this is positive, it's going up from it. So that's why it's greater than. So I draw in the asymptote up there at y equals 1. And having done that, I can then start plotting my points. Now the first point is up how far? How far up is the first point? 1. Because there's no stretch or anything like that that's going to change it, so we start up 1 from the asymptote. That's partly why we draw the asymptote in. Otherwise, we might try to put it just up at 1 instead of up 1 from the asymptote. Right, now from there, as I go to the right, I'm going to multiply that height by what value? Yep, by 2. This number always tells us what I'm multiplying the height by. So remember that idea. As my values increase, I'm doubling that distance from the asymptote. It's going to be an important idea today. All right, so if I start up 1, then next I'm going to go up 2, and then up 4, and then up 8, and then 16, but 16's off the grid, so I stop there. So as I go to the right, as I get bigger, I'm multiplying by 2. What happens then as I get smaller? Divide by 2, yep. So if I'm at 1 here, that means then it's going to be a half, a quarter, and very quickly it's basically right on the asymptote. And so then, having plotted those points so that we can be fairly accurate with our graph, go ahead and draw the curve in that goes through them. Having done that, we're going to use this as the basis for some other work we do. But that work we do is going to be the inverse. And so let's start by actually finding the inverse equation. So, what's step 1 of finding an inverse equation? Well, it's the same as any inverse, right? Swap x and y. That's the big idea of inverse, is it swaps x and y. In this case, we physically do that in our equation. And then, for the equation, then we just need to now write it as y equals. So that means solving it. Well, in order to solve this equation for y, what should I do first? Well, this 1 is in the way. It's not in the exponent or anything like that, so let's move that out there first. Yeah. So I start by subtracting 1 from both sides. Now I have the x minus 1 equals 2 to the power of y. This is as simple as I can make this side, which means I now must use some advanced knowledge. What is that advanced knowledge that allows us to solve for the exponent? Logarithms. Yep. And so I'm going to take the log of both sides. Now, saying that, some of you are looking at this x minus 1 and you're feeling a little pain in your brain. But it's okay, it still works the same way. Because when I go to write my log, we end up writing log. The base is still going to be 2. And the number inside the parentheses is whatever it equals over here. It's just going to be the whole thing. It's just going to be the whole x minus 1 that's in the parentheses. And then it'll equal the exponent. And the fact that it equals the exponent makes our lives a little bit easier, because now we have y equals. That's what we are going for in that whole process. We are trying to get to something that was y equals, so that we could then know our equation. And I wanted to do that so I could graph it. But do we know what the graph of log base 2 looks like? Not directly. We haven't ever graphed one in here before, and yet you can still graph the inverse. How? Yep, point by point. We can go to every single one of these points that we plotted here, and we can swap the x and y coordinates. For instance, the very first point that we plotted was up here, 0, 2. Well, if I swap the x and y coordinates of that point, 0, 2 becomes 2, 0. Remember that when we swap them, I'm only rearranging. Signs do not change. The sign goes with the number. And so then we end up with 2, 0. We plot that point. We know that point must be on our inverse graph. please repeat that process for the rest of the points that we plotted here. Then, when you've plotted all of those points of the inverse, this is what you should be looking at. So check each of those points, make sure you have each of those points plotted correctly. Then once you do, go ahead and draw the curve that goes through them. And so you notice that ends up giving us a curve that looks kind of like this. Now some of you might be wondering about this extra point that I plotted down here. That was just in case you weren't sure, based on these points, what's the curve going to do. I went ahead and grabbed this point out here and swapped the xy coordinates as well, just so I can kind of see about where is that going to end up as well. Helps me be a little bit neater with the graph and know why that's going to be there. So having done that, we've now graphed a logarithm. And so already you can see this is what a log graph is going to look like. And it certainly has some definite properties. One of the properties that it has, though, is one that we haven't drawn on there yet, but that you always will draw on. Because our exponential here had an asymptote. Well, remember that the inverse graph is the exact same shape. And any characteristics that the original has, the inverse will also have. So if the original has an asymptote, the inverse also has an asymptote. Can you see where it's going to be here? In this case, it's vertical. Because that's the line that our graph is approaching, but never really crossing. Go ahead and draw that dotted line in to represent the asymptote on your graph now as well. All right, and then since we started with figuring out where the asymptote was in the domain and range of the original, let's also see what that would look like for our logarithm graph. So first of all, the asymptote. You can see it there. Well, we can see that it's at 1, but how do I make it a vertical line? Is it x equals or y equals? It is x equals. And so our asymptote for our logarithm graph is x equals whatever the number is, every time. And then knowing where the asymptote is, that makes the domain and range easier. The domain. Is my domain going to be all real numbers again? No. My domain comes from the old range. Remember, if I'm just using the technique of switching them. So notice my domain here. It's the x value starting at the asymptote and going to the right, but never actually hitting the asymptote. So our x's must be greater than 1. Same idea as our old range, except we swap the x and y part. And so the range then, what would the range be? Yep, again it comes from the original domain, so the range then, it has to be all real numbers. And we can see that graphically because you see as it's going down, it just keeps going down forever. And as it's going up, it's going over a heck of a lot more than it's going up, but it is still going up. And it keeps going up forever and ever and ever. It's just way over there as it goes up. And so having seen our first logarithm graph, just kind of summarize a couple important points about this. Logarithm graphs will always have a vertical asymptote, every single one. And you notice here that the distance from the asymptote is multiplied by the base as y increases. Remember with our exponential, as we increased, I doubled my height. In the case of the logarithm graph, with being base 2, that means that as I go up, I'm doubling that distance. Both of them, both exponential and logarithms, we could say that as our variable increases, our distance from our asymptote doubles. It's just a matter of which way the asymptote is going. So it is the same idea as the exponential, so if you know exponential, you now know logarithm as well. It's just on its side now. Flipped across y equals x, technically speaking. And so now we're going to be graphing this logarithm equation, and no, I'm not going to worry about doing the inverse first. We can just use the properties that we've just observed about the logarithm in order to be able to do it. Now first up, I want to identify the parent function. Well, if I strip away the transformations, my transformations in this particular example would be like the +4 and the +2. If I strip those away, notice what I'm left with. I'm left with just log base 3 of x. That then is my parent function. And just like when we did exponentials, it always had to be some number to the x. With logarithms, yeah, it'll always be log with some base of x. There'll always be some number in there that defines which parent function it is. All right, now our asymptote. The asymptote, remember, is vertical. And so our asymptote is going to be changed then by how far this graph has been moved left or right. Okay, so which number moves it left or right, the 4 or the 2? It's got to be the one in with x. So yes, it is the 4. So the 4 is moving it sideways. So that means that's moving our asymptote. Which way does a plus 4 move it?
Left.
Left, yes. And so since this moves my whole graph left 4, that means my asymptote is going to be at negative 4. And vertical means x equals. So it's x equals negative 4. Go ahead and draw that in on your graphing grid. Now from there we got to start plotting points. And so wrapping our heads around how do we plot these points? Well, remember with an exponential, and this is very closely related to an exponential, normally with an exponential I would start up 1. In this case, that means I start over 1 normally. But this point has been moved a little bit. It's been moved up or down. Specifically, the plus 2 hanging on the end moves this point up 2. But notice it's still starting over 1. And so that's where your first point goes. So it's saying, normally I start over 1, and I'm just moving that point that's normally over 1 up 2. I've now used the plus 4. I've now used the plus 2. So having drawn this much in, all I need to remember then is what my parent function was. Because that's going to tell me that I'm going to triple my distance from the asymptote each time I go up. And so I start by going over 1. 1 times 3 is 3. 3 times 3 is 9. If I went up again, I'd have to go over how far? 27. Because it's whatever I did before multiplied by 3. And so that's how we get these points. Make sure you got those plotted. And so if I'm multiplying by 3 as I go up, what am I going to do as I go down? Divide by 3, exactly. Just like we do with an exponential. And so then, if this is over 3, then my next one's going to be over just a third of that. And the next one after that would be over grand total like a ninth. It's getting really small really fast though, right? You're really kind of eyeballing these to be only 1/3 as far over each time. Having drawn in a couple points on each side of that first point, we can feel pretty good about being accurate with our graph. So go ahead and draw the curve in that goes through it, remembering, of course, do not cross the asymptote. And so this is what you end up with for your graph. So from here then, let's go ahead and just take a quick look at the domain and range now that we can see the graph and see what's happening in it. What is the domain of this graph? Well, is it all real numbers? No. So I know that the first thing I got to put in there is the x. And where do my x values start? Well, they start at the asymptote. And so it's going to be a -4. The only difference between how I write the asymptote and how I write the domain is the sign that goes in them. Because for the domain, it's not x equals 4. Our x's are getting bigger than -4. So it's x is greater than -4. Remember, greater than, not greater than, or equal to, because it never actually hits the asymptote. All right, so what's the range? Yeah, that one is all real numbers. Because it's going up forever and down forever. Every single log graph will have a range that is all real numbers. All right, so you're graphing this one on your own first. As you do so, you first figured out what's the parent function, kind of know what it's starting from and what it's originated from. Well, in this case, there's no shifts or stretches or reflections. There's nothing in this one. So our parent function is our original equation, which means that my asymptote hasn't moved. It's at 0. Yes, I do like to still draw it in even though it's right on the axis, because that way I can look at my graph and know that I drew it in and didn't just forget about it. All right, so having drawn the asymptote, next up, where do we put our first point? Well, remember, with an exponential, I start up 1. So with a logarithm, I start over 1. And having started over 1, I then can look at the base of my logarithm, which is 4, and I know how far to go over each time I go up. So if I just went over 1, I'm going to go over 4, and I'm then going to go over how far? 16. And then if I had to go over past that, if it actually fit, it'd be 64, and so on. Because I'm taking whatever that last height was, and I'm multiplying it by 4. In this case, though, only the 4 fit. Okay, and then we go the other way. We go down. As we go down, we're dividing by 4 now. So the 1/4, we can plot that one decently, but 1/16 is the next one after that. That's getting kind of hard to be really precise. You're practically right on your asymptote there. And so we very quickly are sitting on the asymptote. Go ahead and draw the curve through it now that we plotted all the points we can. So then, check to make sure that your curve is all looking good. And then we can talk domain and range again. The domain, well, remember, it's all the x's that are greater than the asymptote. Our asymptote here is at 0. So my domain is x is greater than 0. And the range, well, just like every logarithm graph that you will see, the range is all real numbers.